Another way to think about it is this. Force causes acceleration, right? So how is this object going in a circle accelerating? Okay, so let me clean this up a little bit. If you haven't copied that yet, you can pause and rewind the video. It's a good thing about this. Let's think about in terms of acceleration. How is the object accelerating? Now, at first you might say, well, you're going in uniform speed, right? You're going at a uniform speed, so there should be no acceleration. But you remember acceleration is also a vector quantity. So there's a direction and a magnitude. So the magnitude of actually the velocity, right? The velocity is changing. The speed is not changing. So there is an acceleration. Now the question is two things. The question is, what is the magnitude of that acceleration and what is the direction of that acceleration? Okay, let's talk about direction first. Okay, so what is acceleration? Well, acceleration is the change in velocity over change in time. Oh, this is average acceleration. The instantaneous acceleration should be defined, right, as the rate of change of the velocity. Okay, but you understand this is just the limit of this. This is the same thing as saying it's the limit of the change in velocity over time, where you take a short enough amount of time, right? It's really just the change in velocity. So what is the change in velocity? Well, I need the initial and final. So that's the initial velocity. After a while, let's say it has went over here. Let's find the average velocity first, right? Average acceleration. So here, if this is my VF, so what do I need to do? To find the acceleration, I need to find VF minus VI, right? So the acceleration, notice this is a scalar, delta t is a scalar. So the direction, if I'm curious about the direction of A, I need to find the direction of delta V, which is the direction of this vector, right? VF minus VI. So what's VF minus VI? Well, if they're in different place, I can't really do a subtraction. I need to first move this over here, right? So move this over here, then I can start talking about subtraction, okay? So move them to the same point. Now subtraction is really just adding negative vector, right? So what's negative VI? Well, negative VI is flipping the direction down here. So this is negative VI. All right, so VF plus negative VI, I can now put them head to tail like this, right? So VF minus VI will give me an average acceleration pointing this way. Okay, but this is average, right? Now, what I need to do is to take the limit to find that this is the average acceleration from this point to this point. Okay, slightly counterintuitive that it's pointing this way, but let's find the instantaneous acceleration at this instant. So what do I need to do? I need to shrink the delta t to 0. So now I'm waiting for really quite a long time before I do the subtraction. Let's see if I wait what happens if I wait a shorter time. If I wait for a shorter time, this is my VF, right? So instead of having a VF that goes horizontal, I should have a VF. Let me put that over here, right? So what's the length of this arrow? It should be the same as the length of this arrow. I probably couldn't draw it to scale, but you can imagine I have, right? This length should be the same as these lengths, right? Because the speed is the same, so the magnitude of these is the same. All right, so VF minus VIR, that's our goal. We want to find the direction of the acceleration. So minus VI, all right? So if I take this length, this is tilted, so it's somewhere like this, right? Minus VI. Okay, so VF minus VI, all right? So that's the acceleration, okay? But still, that's not taking the limit of delta t all the way to 0, right? So now I need to do better. But now remember, what was my first acceleration, right? My first average acceleration was over here. Now it's like this. Now, if I shift this a little bit closer, right, you see that's now the VF. It should be the same magnitude of this. But yeah, you can imagine that is. So how would this look like? So if I take that over here, so now it looks like this, right? So this is my VF, and my minus VI would take me like this. So the A would be like this. Okay, I won't start labeling them because they'll start to all overlap each other. And so notice I went from here to here to here, and the acceleration vector, the average acceleration vector, I should put a bar on top as well, but not enough space. So it went from here to here to here, and the moment, so yeah, if I keep shrinking delta t to 0, so I should measure the acceleration at this instant, right? So I shouldn't wait too long. So at 0, as I keep moving this over here, at some point you see the A vector would be pointing perfectly towards the center. Okay, so that's the acceleration. You see that what does that mean, right? You might also wonder, oh, is that length 0? But not quite, because it looks like it's getting shorter and shorter, but time is also getting smaller and smaller. So acceleration should be this magnitude divided by this magnitude, right? So a small number divided by a small number, no one knows what that is, right? 0.01 divided by 0.01, it's 1. Or 0.01 divided by 0.0001 could be 10 or 100 or 1,000. You can divide two small numbers, it could be big numbers. So no one knows what it is, but what I do know is the direction. That was what I was trying to find. The direction of the acceleration is this way. Okay, so mathematically you see that, but what does that mean? That means that what the acceleration is doing is it's changing just the direction of the velocity vector. Okay, it's purely in this way. So just with the same way as force, if I have an acceleration that goes this way, then you can break it down into a radial part and a tangential part. But the tangential, let's make this components, right? So the radial acceleration will cause the velocity, because remember the velocity vector is also going forward. So the object's trying to go forward. If I have any tangential acceleration, it's going to make it go forward faster. But that's not what we want. We want a uniform speed. This one, the AR component, right? If I break it into these two components, the radial component does not accelerate the object. All it does is it changes the velocity vector's direction. Okay, so what we want is an acceleration that is in the radial direction and no tangential component. So we want a purely radial acceleration, or also called centripetal acceleration. Okay, so acceleration is the same thing as centripetal force. So that's another way to see that. And if there is a centripetal acceleration, you can ask Newton, well, what causes the acceleration? And Newton will tell you, well, any acceleration is caused by a force, right? So we can write it like this. Any accelerations caused by a net force. So if you want a centripetal acceleration, you better have a centripetal force. Okay, so that is the key concept of circular motion. You must have a centripetal force, and to cause a centripetal acceleration towards the center, then the object will keep going towards the center. That's the whole idea. Okay, makes sense? Now, the next question is, what is the magnitude of it? So just to keep things simple, at least in the first part, I will just tell you the formula of it. And I'll only explain where it comes from if I have time at the end. Okay, so this will allow us to work with it, get a little bit of better sense with it first, and to worry about the way how I come up with how we figure out the formula, which is a little bit convoluted, and it may distract you from the real physics of this. Okay, so the magnitude of A is V squared over R. Okay, and be careful whenever you use this formula. This is the centripetal acceleration. I highly recommend putting a subscript C over here when you write this down. So this means sometimes I even make sure I understand it's centripetal by labeling it a little bit more. Centripetal acceleration is the V square, so that's the speed square. Notice I said speed, not velocity. It doesn't matter, because if you square it, it will always be the magnitude square. Okay, a vector you can't square a vector. The only sensible way, another way of saying it, we haven't really talked about squaring vectors. There is a way to do it. The only sensible way is to square its magnitude. So that's really, and you notice there's no vector signs everywhere. So this is talking about magnitude. All right, couple of comments. Make sure you understand this is magnitude of A, right? This does not say that the acceleration is in the direction of v, okay? So that's not the point. We spent the whole 10 minutes talking about the direction is towards the center. It's the magnitude is equals to this combination, v squared over r. Commit this to memory, right? V squared over r. Not too difficult, but just remember it. It's the speed square divided by r, and r is the radius, okay? So does it make sense? So I'm not gonna prove it right away, but it just, let's see if it makes sense. Is the faster it goes, the larger the acceleration it has to be, okay? Maybe I should give the centripetal force as well, but it's simple. The centripetal force is mv squared over r, right? So basically it's ma, so if the centripetal acceleration is v squared over r, the centripetal force is mv squared over r, okay? So let's see if that makes sense. How much force do you need to make it go in a circle, right? That's the force that's pulling things to the center. Everything I'm writing is a magnitude at the moment. You see no vectors over here, right? The faster it is moving, the speed, which speed, it doesn't matter because it's a constant speed, it's uniform speed. The faster the speed, the more force you need to pull it to the center, right? That kind of makes sense because faster the speed, there's more inertia. So in order to imagine swinging a rock around a rope like that, right? If you swing it faster, you need to tug on this higher tension. You need to tug on it stronger and stronger to do that. The larger the mass, you need more force, right? The larger the rock, if you swing it in circles, you need more force. And also, interestingly, I think you can imagine the smaller the r, the larger the force. If you want to swing it in a very, very tight circle compared to a very, very large circle, put a rocket somewhere else, right? This is at the end of a rope, and try to swing it with large circle compared to a very, very tight circle. You need a much higher centripetal acceleration or centripetal force in order to make it go in a tight circle. Okay. All right. So we'll look at a couple of more jargons around this, and we can take a look at some classic problems about things going round and round.